and start. Okay, so another try. Welcome everybody to today's lecture on short-term memory. And I do apologize so that the slides have been online rather late, but I have been sick a little bit, so I just finished them literally at that point. Okay, so let's, as usual, start with an introduction into short-term memory. And as always, let's start with a video clip. I hope I find everything for every topic, but as you can see, for short-term memory, it's quite easy to find something. So let's have a look at poor Dory.
Sorry, I didn't see you, sir.
He's gone. No, away. I need to find the boat.
Oh, hey, I've seen a boat.
You have?
It passed by not too long ago.
A black one?
I'm Dory.
Where? Which way?
It went, this way, follow me.
Thank you.
No problem.
So you probably know the story. The little child of that fish has gone now and is trying to find it. Okay, so this little video clip shows and demonstrates actually how essential short-term memory is for our everyday lives. Because if you're not able to keep information alive and available for a short period of time, we would actually get lost. We want to pick something up from another room, we go over there, and we can't remember what it was. I mean, we actually know that from our everyday life, but usually it works. And somebody tells us a phone number, and we even can't write it down because we would have forgotten it already. So short-term memory is really something which we demand or use, let's say, every second of our life, unless we're asleep. So let's have a look at this concept today. In general, just to give a little bit of context, we have a couple of different stores in memory in a larger sense. The first thing where sensory information comes in, this is then stored in so-called sensory stores. And they hold information very briefly, so less than a second. And this is specific to each sensory modality. So, for instance, we have an echoic store for auditory input and an iconic store for visual input. But that's not what we talk about. We talk about short-term memory, which then is a little bit longer. This holds information in the order of seconds or minutes, depending on the theory and the background you're looking exactly at. And it has a limited capacity. So we can, as you may know, not store unlimited information in that short-term memory. And finally, and that will be the topic of next week, we have long-term memory. And here we can hold information over very long periods of time. And the assumption is that it's basically unlimited with respect to its capacity, so that we can store as much information as possible. And our aim here is, of course, that all the knowledge you gather during your study time finally ends up in long-term memory. So let's have a closer look at short-term memory. There are a lot of different terms around, sometimes called primary memory, active memory, or immediate memory. But in the last 10, 20 years at least, the most common term is definitely short-term memory. There's a slight distinction to working memory, which we will see later. And a definition of short-term memory would be, or one of the possible definitions, that it is the capacity for holding a small amount of information, so this capacity limitation, in our mind in an active, readily available state for a short period of time. So we have a bit of information which we have highly active and available for a bit short amount of time. That is basically what our short-term memory is. Okay, so a lot of you did the practicals just last term, PY2025. And a lot of you then used actually short-term memory tasks in your paradigms. And one of the basic ideas, or to sensitize you to this paradigm a little bit more, I would like to do this exercise. And the question is, how would you investigate short-term memory? And there's probably a very basic task in that. You present something, ask people to remember that, and then you ask for them to reproduce that somehow. However, when you think about this in more detail, and that's exactly what I would like you to do now in groups of 2 to 3 people, think about, okay, in this very basic setting of a short-term memory task, what parameters could you change or vary or manipulate in that task? And it's really about the task, not that you say, well, I could remember words, I could remember pictures or something like that. This is more the content, but about the method, about the task itself, and try to discuss what potential effects that may have on the outcome of your task. And I would like you to post the answers then to Poll Everywhere, so that we can see and have a look how many different parameters there may be in such a simple thing as a memory task. And just to give you an example, one big differentiation or one big parameter in these type of tasks is, how do you ask participants later, how do you assess the memory performance? And one could be free recall. You could just give them a blank sheet and let them write down. And the other one is, lost here in the whiteboard, is recognition memory. That means you present them items and you ask them, have you seen that before or not? And they just have to say yes, no, or give a rating of their certainty or something. So this could be one of the parameters, and there are probably many more. So go get together in groups of 2 to 3 people and think about, and there are no wrong answers, just try to think of everything conceivable which you may manipulate and modulate, and I will try to activate that poll. Okay, 28 responses so far. Can we get any more? 29. Okay, let's have a look what people wrote. No, that. That's probably immediate recall or not. Information type. Yeah. Time interval. There are a lot of time intervals involved here. Depends on which ones you mean. Number list with probe numbers. That's like a recognition task. Emotional versus non-emotional intensity. This is more about the material, the content. Again. Impact of personality. Again, not really the task. Time of day, possibly, yes. Word lists and number lists. Okay. Interest and investment in content. Okay, I'm not sure I made myself clear. I was really looking for specifics of the task itself, so parameters of the tasks. So this time periods, where so far the main thing I would say it's the timing issue. Number of words, that is a parameter. Possibly. So how long are your word lists if you use something like that? How long between presentation and recall? Whether you have a retention interval or not? Yeah. So things like that. Okay, environment, gender. Yeah, these are always then parameters which may affect the memory score, but which are not specific to the task. Survival relevance of the stimuli, gender and age. Okay. Good to know. Next year we'll try to make it a little bit clearer then. Okay. So, let's go through a couple of parameters I came up with. So when you have a traditional short-term memory task, you usually have at least 3 phases. And the first one is the item presentation phase. And that is a stage where the participant encodes the information into short-term memory. So you have to encode information here. And as parameters, and this is not an exhaustive list, but these are typically the key parameters in the studies if you look up in the literature. But you could find probably a lot of further additional parameters here, sometimes more fine-grained. For instance, do you present all the items all at once on one sheet of paper, or item by item on a screen, for instance? What's the duration of the presentation of each item? One item every 2 seconds, one item every half a second. The interval between 2 items. Do you give the participants a little bit of time to try to properly encode the item, or do you really flood them with the new items one after each other? So, and this all has potential effects. If you have a very high pace, participants can't work with the information but just have to try to keep it online a little bit. Then you have a retention interval, possibly. This can be 0 So after item presentation, you would just directly start the recall, or you have some time where you ask the participants to keep the items in memory before they are allowed to recall. So this is the active storage component. And if you, for instance, have single cell recordings in monkeys and you want to search for neurons which are involved in short-term memory, then often you look at activity in this time period, where you don't have any stimuli, you don't have any action output, you just have this keeping information active. And parameters are, of course, duration. How long do they have to do that? And the second big thing, if you try to think about how you would do the task yourself, is whether you allow rehearsal or not. So rehearsal meaning, let's say you give them a word list, that they are allowed to repeat that in their mind, or whether you not allow that. If you do not allow that, you can prevent rehearsal by adding a task. For instance, to say, okay, during the retention interval, please count backwards in threes starting from 397 or something. And then they have to say 397, 394, 391, and so forth. Or a very simple task would be, please say the word the repeatedly, like the. This also already occupies your rehearsal process so that you can't do that. And this will greatly affect the outcome you have. And then finally, you have the test phase, where you want to assess the memory. So the participant now has to retrieve the information from short-term memory. And parameters, the example from before, do you do it as recall or recognition memory? And these are rather different approaches to access memory. And one thing which is often introduced or incorporated as well is whether participants have to recall the items in the exact order they learned that. And this is called serial recall. Or do you allow any random order? Do they have a time limit to recall? And especially if you have recognition, you can measure response times. How quickly did they say, oh, I have seen this before or not? And if you just have them writing down, you usually look only at accuracy. How much % correct do they have? How much items did they remember? So just to show you what is the typical approach to investigate short-term memory, but also in a more generic sense about where you might think, okay, that's such a simple task to do, how many variations you have, how many parameters you have to consider when you design such a study. Okay, so let's have a quick demonstration and try it for ourselves. And I hope you all have something to write with you. So either a sheet of paper and a pen, that would be the best thing. And just keep it out. We will have a couple of recall tasks today, short-term memory tasks. The sheets will stay with you. I won't collect them and give you like a memory score in the end or something like that. And if you want to, you could of course also use a computer or something like that. Okay, so please get a sheet of paper and a pen. And you will see 12 words for 2 seconds each. And at some point it will say on the screen, please write down the words. And then please write them down. And you can do that in any order you want to. Please don't do that together with your neighbor or something. Just do that individually. And then let's take it from there after you've done this. Okay. So you can use any order. Oh, sorry. Started already. Okay. Is everybody ready? Okay. So then ready, set, go. Okay, so these were the words, and I would like you to ask to go to Paul Everywhere. And please, it's a multiple choice thing where you can select multiple answers. Please select every word you remembered, okay? And please be honest. I'm curious to see whether we see a certain pattern in the results. Okay, so it's not changing too much anymore. I was hoping for a slightly different pattern, but let's just a little bit over-interpret that data, so don't do that with your real data. So what you typically would find if you do like a proper experiment of that type is that words in the beginning and words in the end are usually better remembered. You can see that here. The first word is the best one, and the second one is also quite high. Dress is still very high, maybe because we had a dress story, let's say, in one of the previous lectures, and it was very highly stimulating for you in that sense. And the last one is at least much higher as the last but one, but not very much as the other ones. So often this is what happens, and okay, so that the first and the last words are remembered somewhat better. And the first one to observe that was Hermann Ebbinghaus in the late 19th century. And he did a lot of research on memory. So his participants had to learn endless and endless lists of words and just random syllables and stuff like that. And this is one of his findings. So the position in the sequence, so these are the first words, these are the intermediate words, and these are the latest words. And then how good is the relative recall in percent here? Then you see that you get usually such a type of U-shaped curve, which is called the serial position curve. And there's two effects here, which are called the primacy effect in the beginning, that you're better, and the recency effect, that you're better in the end. And the explanation for this is, for the primacy effect, that you remember the first words better, is that a lot of people follow a strategy of rehearsal. So you see the first word like fashion, you start fashion, 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 and then the next word comes up. I think it was endorse. So you do fashion, endorse, fashion, endorse, fashion, endorse, until the third word comes up. And by this, naturally, the first word has the most repetitions of all. This is one thing. Another explanation is that you just have more time to invest some deeper encoding. So to work with the word and say fashion, okay, I get to create an image for that in my mind, or something like that. And these two effects together contribute so that you have the first words are remembered better. On the other hand, the recency effect is that, so by this, what we do here effectively is, in the primacy effect, that we start to transfer the words into long-term memory. And therefore, later during recall, we can access them more easily. The recency effect is that the last words are just still very fresh in our memory. They didn't fade away so far. They were not subject to any interference from follow-up words or something like that. And this last bit, the recency effect, is greatly reduced or even eliminated if you introduce a retention interval. In particular, one where you don't allow rehearsal. Then the curve is like this, but it's just flat in the end. Because then you don't have this effect of it's just still in memory, because it also was like 20 seconds ago. So this is now, you've seen one of the most prototypical approaches to investigate short-term memory, and one of the most prototypical findings when you go through word lists, these type of standard learning. And of course you can do the same thing with pictures, with numbers, and all different types of stimuli. But the logic basically stays the same. Okay, so to summarize, we've seen that short-term memory is a capacity-limited short-term store, and that a typical short-term memory task has 3 stages. We first start with the item presentation, then we have potentially a retention interval. In the task you have just done, the retention interval was 0. Directly after the last word, I asked you to recall. And then you do recall recognition. And yes?
It's strictly 0 because there's the writing time involved.
Yes, that is right. And you could also say from the first word until then, it's not 0. But again, from a methodological task description perspective, it's not 0. But you are right in when you look at, when you want to investigate the, or predict the performance on each item, then you would have to say, okay, when did I present? When did I ask to recall, and when did the person actually try to recall? So the writing takes time as well, yes.
So I certainly wrote down the last words first, basically the recency.
Yes, I mean it's different for different people. They would take different strategies, yes. Some would say, okay, I just saw that, so I write that down first. And others may say, okay, let me write down first the ones I've seen first, because otherwise I may forget them, and I may remember the last ones easier. So these are strategy differences then. Okay, so we have these 3 different functions. So when we want to describe a cognitive architecture of memory, then we have to incorporate the encoding, the storage, and the retrieval processes here. And the final thing, when we do a free recall task with immediate recall, then we see this U-shaped curve with the primacy effect, which is indicative of long-term storage, and the recency effect, which then shows the short-term memory storage and these type of tasks. Do you have any questions on this introductory part? Okay. So, let's get to the next chapter. Again, let's start with a little exercise. You need your sheet of paper again. Okay, you will now in a moment see, for quite a while, I think 15 seconds or so, a very long string of letters. And there are too many to remember, but please try to memorize them, and this time in order. So they are from left to right. Just try to memorize as many of them in order. And once you're asked to recall, please write them down again. Okay? It may start already now. Let's see. Yep. Okay. Another demonstration. So, same task, again, exactly as before. Okay? Again, as many letters as possible. Okay. Who did remember more letters in the second time? Letters. Just raise your hand. Who remembered more letters in the second time? Yeah. Okay. So, most people probably remember much more because when we go here, you will see that you actually see words: pack, load, fill, keep, for, mass, book. The letters were actually the same in the preceding exercise. They were just scrambled from that. So this shows that our short-term memory, it's not just the basic information, or we have to look at how do we define information which we can store. When we say, well, there's a certain limit on the amount of letters we can store, we clearly saw this is not true. In this instance, you can just remember much more letters. The reason is that we were able to chunk the letters into words. And this is this chunking hypothesis, and I'm sure most of you have heard of that before. So, just as a quick final demonstration, again, same task. So, probably even easier. I hope so. So, this time we were able not only to chunk the letters into the words, but even to chunk the words into the sentence, which is very well known to most of us. And then we just have this information in our mind. And George Miller was the first one who proposed this chunking theory in his very, very famous paper, The Magical Number 7 plus or minus 2, Some Limits on Our Capacity for Processing Information. And this is probably one of the most cited papers ever in psychology. And like 2 or 3 years ago, it has been cited over 18,000 times. Cited meaning properly cited in other scientific articles. And he had this observation that the amount of information which we can store does not directly or is not easily quantifiable by things such as letters. So information is such how a computer would define information in terms of bit or something, but on how we can chunk or group this information into chunks. So what is an official definition of a chunk? And a chunk can be defined as a collection of elements, such as letters, which have strong associations with one another, but weak associations with elements within other chunks. So like in a word, when the letters can be grouped to a word, we group them together and they have a close association, but a loose association to the letters of the other words. So a word forms a chunk in that example and respect. And these chunks are based on previous knowledge. So we have to learn that. We first have to learn the letters, then we have to learn the words, like when we are children, and we have to know the quote to be able to chunk that into a sentence. To a person who never saw this sentence, this quote, the final demonstration before, the task is not much easier than the one before, where we had unrelated words with each other. So it's previous knowledge. And Miller proposed, based on his research, that the capacity of our short-term memory is 5 to 9 chunks. That means, as an average, as a rule of thumb, 7 plus minus 2. And this is really no strict limits. So there will be people who have higher and people who have lower limits. And there's a lot of follow-up research on that, which really deals with this idea of chunks. And although it's very fascinating and attractive and appealing, it may be a slight oversimplification of the truth, because when you look in a very close detail, it becomes difficult to define what exactly a chunk is and how participants really form chunks and use chunks there, and whether the limit is really here. Others proposed that we actually can remember only 3 to 4 chunks if you control for certain further things which may help your memory performance. So the key thing to understand or to take from this story is that our capacities very strongly depends on how we process and group the information we want to retain. Okay, so a study supporting or providing evidence for chunking, investigating that. So the participants had to remember always 3 letter pairs or more of that. So it could be, in this example, it were pseudo words, consonant, vowel, consonant pairs. And in the first condition, they always had these 3 letters, and because you can't group them to a word, you could say you have 3 chunks of information. Then you have a second condition, where you just get 3 letters again, but this time it forms a proper word, like dog in this example. So like here you have 3 letters, but you only have 1 chunk instead of 3 chunks here. And the third condition was that you actually have 3 proper 3-letter words, dog, bar, and pet. So you have 9 letters, much more than here, and 3 chunks. More chunks than here, but the same number of chunks here. So the question is, what did they find? And I already said that it's evidence supporting chunking. So try to think which 2 conditions have to be equal in terms of performance, or are they all the same, to conclude that it supports chunking. And again, it's a poll everywhere question where you can give your answer. I just have to activate it. I will switch back in a moment so that you can see the different conditions. Why does it always here? So I hope I made myself clear. The question is, which 2 conditions should be the same to support the idea of chunking? If you want to, you can discuss with your neighbors. if you came to an answer, don't forget to put it on poll everywhere. Okay, we already have 50 responses, so have a look. So more people want to vote right now? 50? Nothing coming, so let's have a look. So, most people say 1 and 3, and quite a few people say 2 and 3 as well. So it's a roughly even split. Let's have a look at the conditions as well. Okay, so the split was between 1 and 3 and 2 and 3. So if these two are the same, why would that support the chunking hypothesis? Here we have 3 chunks as compared to 1 chunk, and we have 9 letters as compared to 3 letters. So if you measure information content in form of letters, you have more information to remember here than here. And if you measure it in forms of chunks, then you also have more here than here. So these two should not be the same if you think that chunking takes place. Actually, these two should never be the same. If you would say, no, chunking is not true, it's just the basis of raw information in forms of letters, these two should be the same, 1 and 2, because you have 3 letters in both cases. If the chunking doesn't matter. If chunking matters, then this one with 3 chunks should be the same as this one with 3 chunks. And that's actually what has been found indeed. So condition 1 and condition 3 show the same performance in participants, which shows it is not about the raw information, as you have just experienced yourself. It is about how you can chunk the information. Okay, any questions on that? Yes?
Sorry, was that answer 1 and 3?
1 and 3 are the same.
Was the right answer?
Was the right answer was 1 and 3, yes. Okay, says here as well. Okay. So to summarize that, by the use of chunking, we can group units of information into groups which we can later on then use as units themselves. So that makes it possible. And chunks themselves are long-term memory structures that have been learned before. And if you remember, long-term memory is supposed to be capacity unlimited. So we can store an indefinite number of chunks if we wanted to. And our short-term memory capacity is mainly limited by the number of chunks we can memorize. So we can potentially appear to have a huge short-term memory capacity just when we are lucky to be able to use a lot of chunks in the given task or something like that. And yes?
I believe there's a difference in recall if, I think it's if you can pronounce a non-word versus if you, so this was X, U, W, and therefore you
yes.
could say U, whereas if it were 3 consonants, it would be very hard to say. Does that indicate that this, that it's necessarily a long-term store then? Are you encoding it as long-term then and there?
You mean the reason why it's pseudo words is to make it comparable to the other to the proper words, so that you can't argue, well, you have a better memory for words because you can pronounce them. You can say dog, and for instance, rehearse as dog, dog, dog. You have the same option for pseudo words, and the reason is the pseudo word is not part of your long-term memory. So it's not a chunk in itself. You have to memorize it as 3 letters to then later on recall it. You can't retrieve it from your long-term memory. Of course, the result would be different if you allow a strategy which during encoding gives the participant the opportunity to learn it as a new word and put it into long-term memory. So it has been shown that chunks, new chunks, can be formed and learned as quickly as 5 to 10 seconds. And then you would have the same performance as it would have been a word. It actually is then a word. Yes?
My observation would be that it's not just words which a chunk, numbers can be as well.
Of course, numbers, like your own phone number would be a chunk, for instance.
I work to 19, powers of 2.
Sorry?
I can regurgitate powers of 2 because I work to 19.
Yeah, or by powers of 2. Yes, you can chunk in anything where, which makes sense to you. And that's the point, that it is learned. So different people use different chunks. These examples work very well for you, but consider for people who don't speak English, the demonstrations. There are no chunks. It's just random strings of letters in all examples. So that makes a big difference. Okay, any other questions on the chunking? Okay, then I would like to go through 1 or 2 of the short-term memory models which have been proposed before we go into the break. Okay. The first model I would like to propose, or not propose, to present, has been proposed by Atkinson and Shiffrin as early as 1968. So it's really one of the very first information processing models in cognitive psychology. If you remember, that was also roughly the year where the first textbook on cognitive psychology has been published. So this is just at the birth of cognitive psychology. And it has been called also the Atkinson Shiffrin model or the modal model. And it has been very, very influential in psychology because it was one of the first models. It's a rather comprehensive model. Nowadays, we will see it's a little bit outdated and not entirely accurate. Okay, so basically their model is a cognitive architecture of the mind with 3 major stages. The first stage, kind of as usual, as you have seen a lot of times, input is received from the outside world. This input then generates some type of cognitive processing, and finally we produce some output, behavior, by that. And that is a general thing of one of the key things what our mind is actually doing.
Is that model used in relation to attention?
Attention is part of the model, but it's not an attention model, no. And in this model, we have memory stores, which are different places where information is maintained, processed, and stored. And we have so-called control processes, which regulate how the information flows between the different stores and how it is processed. We will go through that in a little bit more detail in a moment, so then it becomes, I guess, a bit more clear. So the whole model, so to say, starts that we have some sensory input, some stimuli from the outside, and as we said, one of the first things in virtually all models are the sensory registers, where it comes into like the echoic and iconic memory, where the information is kept alive for a couple of 100 milliseconds only. And here would be the stage where attention filters which information comes into short-term store. If you believe in early models like Broadbent's or Treisman's models, then you have attention working here, and then you have the short-term store. This short-term store is assumed to be modality independent. That means we have one store for auditory information, verbal, visual information, spatial information, and so forth. And when we want to keep information alive, like in a short-term memory task, we have such a rehearsal buffer. So That's what I just said. We have all information. And they proposed, along with the findings of Miller, that the memory span is around 7 items. And so that we don't forget, we need this rehearsal buffer, so an active process here. Now the next element here I would like to introduce is the long-term store. So according to this model, information which we want to store for long-term has to go through our short-term memory. This has been challenged with newer findings, that we also can place information or store information in long-term memory, actually bypassing short-term memory. But in that model, only information which is in short-term memory can be stored in the long-term. So, and in long-term store, information is stored permanently, as the name already suggests, and the capacity is assumed to be infinite. Okay, and this is finally the whole model. So we have had a look at the central part so far. We now see that we have additionally these control processes which kind of regulate the input into these stores, for instance by means of attention from the sensory registers and from long-term memory. So long-term memory retrieval would place information from here to here. And these control processes also select which cognitive operations do we hear with the material in short-term storage. And an example could be mental arithmetics. So that you say 50 plus 5. So the operation is to add the two numbers and retrieve possibly the solution from long-term memory, like we spoke about last week. Or otherwise to do a different operation to subtract that, or maybe control processes in the form of delete information from the store or things like that. And then finally, based on the information in our memory systems, we generate a response. That means we show behavior as human beings. So that's their basic information processing model, where memory, and in particular short-term memory, has a very central component in. However, they had a couple of incorrect assumptions. The first one is that short-term memory is modality independent, and as we will see later, we nowadays know that at least two different types of information is stored in distinct subsystems. This is verbal information and visuospatial information. And the second one is a little bit along the same lines, and that is that they would propose that short-term memory, that means the maintenance and the processing aspects, is a unitary thing. So if you maintain something in memory, this will cause problems with processing information. However, it has been shown that this is not the case. Under certain circumstances, we can do two things in parallel here, more or less. So we don't have to go into too much detail about the criticism because it is a rather old model. The key message here is that it is more complex than their model initially suggested, and that's a typical way. You start with a rather easy and simple model, and then you have to accommodate new findings, and models become more complex. Okay, do you have any questions on the Atkinson and Shiffrin model? Okay, yes?
I was just thinking of the central executive. Where does that, is that kind of part of this model? Or?
The central executive system is more linked in the Baddeley model, which will come after the break. But the relationship would be the control processes here. This would be the equivalent to the central executive system. Okay, before we go into the well-deserved break, one more type of models, because it's just one slide, and then we can dive into more detail into the Baddeley model and look at verbal short-term memory. Okay, so there's a different concept of whole category of models and we will look at one as an example of these. And these are called unitary store models. And they are really what this name suggests, that they say there's only one store and not more. And Nelson Cowan was one of the persons suggesting these type of models. And the idea is that we basically only have a long-term store. And this long-term store stores all information which we have. Now, what we can do now is that we activate certain portions in our long-term memory. And these activated parts, they are constituting our short-term memory. So that he would say short-term memory is all information in long-term memory which exceeds a certain activation threshold. And so very new information which may come in is placed in our long-term memory, but if we don't use it and rehearse it and work with it, it will after some time again be deleted from long-term memory. So it's not a model which suggests that we store every information permanently forever. It just is a model which has a certain amount of flexibility in the long-term store. So that we have this active proportion, and then we can put our attentional focus on a part of this short-term memory. This is then the focus of our attention, and with this information we can actively work and do something. That's his suggestion. However, the representation here in this cognitive model is always the same. It's not that a certain word is retrieved from long-term memory, placed in short-term memory, like downloaded and uploaded again. It's just you have this one store and you have this word represented, and you just activate the present representation, and then it becomes available to our conscious access, to our short-term memory. And then when we used it and we don't need it anymore, the activation threshold goes down again, but the memory stored, the representation, the trace, the record is always the same we are working with. So this is just a very different concept of how our memory works. And as you may imagine, discussion is ongoing how much remit is in these type of models, and there is evidence which give a certain which say there is some merit in them. However, there is also conflicting evidence which suggests no, short-term memory actually is a distinct thing. For instance, patient studies where you see patients which have a very clear short-term memory deficit without having any long-term deficit. However, as usual, you can try to argue back and forth. Just for you to know, there are very different approaches to describe short-term memory. We will have a break now, and afterwards we will speak about the working memory model of Baddeley. Can you pass them around? Hi, can you pass them around? Hi. Just 1 second, let me stop the camcorder. Yeah. Let's go on. Okay, let's speak about dry throat, sorry. So in 1974, Alan Baddeley and Graham Hitch proposed a working memory model which kind of replaced the Atkinson and Shiffrin model, and it is based on their ideas and their concepts. However, they found some experimental evidence which was in disagreement with the Atkinson and Shiffrin model, so they took that further. And especially Alan Baddeley is a person who really spent a lot of, dedicated basically his whole life on researching memory, investigating memory, wrote textbooks, and did numerous studies with healthy controls with patients and so forth. So if you're interested in memory, in particular short-term memory as well, then this is one key person to start with. Okay, let's have a look. Oh, before we go into the discussion, it would be important to say that what Baddeley and Hitch suggested is a working memory model. And although some people use the terms synonymously, nowadays probably most people would agree that there is a distinction between the two. But it's very important that you are aware of that, and that you try, if you read something about that, in particular the term working memory, that you try to understand what the author actually means, what concept they refer to. So one thing is short-term memory, of course, which is the short-term storage of information. And an example is if I tell you a phone number for you to remember, and you are looking for a piece of paper until you can write it down. So you have to keep it active in your mind. This is short-term memory. Working memory, on the other hand, is short-term memory as well, the short-term storage of information. However, in addition, it is the capacity to manipulate this information. So the example with the phone number, I tell you a phone number, oh yeah, please, it's a 555-3421, and you're looking for a piece of paper to write it down, and then I say, oh, I'm sorry, I made a mistake. In the end, the two digits have to be reversed. It's not 21, it's 12. And then you have to actually manipulate the information which you have stored in your memory and reverse the last two digits. So, as I said, just be aware, for some people working memory is just the short-term storage component. However, nowadays I would say for most people it is this short-term storage and manipulation. Or other people would say storage plus controlled attention, controlled or executive functions which come with that. Okay, let's have a look at their model. They started out by proposing that we have two different storage systems depending on the type of material. And the first system they proposed is the phonological loop, which is, so to say, our inner voice. It is the storage of language-based material, it's speech-based encoding. The second major component is the so-called visuospatial sketchpad, sometimes called scratchpad as well, VSSP. And this is the equivalent for visual spatial information. So our inner eye, if you want to say so. So visual semantics, visual and spatial coding. For instance, when we do mental rotation, this is something which is done in this visual short-term memory. And then 15 years later, 25 years later, in the year 2000, Baddeley proposed a third component, which is called the episodic buffer. And this is thought to account for a number of findings which were difficult to explain with just these two components. And it is kind of an integration hub of information, where information from the phonological loop, the visual spatial sketchpad, and the long-term memory can be integrated and, for instance, used to generate a holistic experience of something. So when we see or retrieve the memory of a person, we get like the voice of the sound of his voice, the visual appearance, and some long-term memory traces of that. This can all be bound together in the episodic buffer. So that far is just short-term memory. In addition to these short-term memory components, these episodic buffer then interacts between them, is a control unit, which is called the Central Executive System, or short CES. And this control unit is proposed to be modality free. That means this is independent of whether it's phonological or visuospatial. And it's basically controlled attention, which controls these sub-processes. It's a supervisory system which determines which information goes into long-term memory, which information to keep online, which may initiate a rehearsal process, and things like that. We don't go into any more detail on the CES here today. We'll look at the other systems more. Okay, there's a number of evidence, and as I said, in particular, Baddeley spent really a lot of time in finding evidence, and the key idea is to use dual task paradigms. And the assumption is, if you combine two tasks which demand the same resource, you will get interference and you become poor at the tasks. However, if the two tasks demand different resources, so they have, so to say, different processing units, then they can work together roughly in parallel and with less interference than you might expect. So Baddeley combined a lot of different tasks with each other to see where do we get interference between the tasks and where can the task roughly run in parallel without interference. And for instance, just to give you a couple of examples, if you use as a primary task a short-term memory number recall, as we have seen here already today, and as a secondary task, a lot of other complex resource-demanding tasks, for instance, reasoning tasks, which demand more the central executive system, then you can see that they nicely work in parallel. In Atkinson and Shiffrin's models, the stores, or the short-term memory, stored and processed information. So storage and processing should interfere with each other in their model. However, it didn't. Baddeley and Hitch found that you can do them largely in parallel. So this is evidence that, and you find the same thing if you do a visuospatial task here. So that he found evidence that this central executive system is really distinct from the pure short-term memory. So the working memory really is a component of at least two things: storage, maintenance, and manipulation. Okay. So the same logic they applied for the short-term memory systems. So suppose you do as a primary task a verbal short-term memory task, let's say again a number recall task, and as a secondary task, well, let's say you do again a verbal task, maybe not number recall but word recall, then you will see that you really struggle to do that task, because both tasks demand the phonological loop and people have severe difficulty with that. You get interference. However, if the secondary task is a visual spatial task, such as a quasi-block task, then again you observe surprisingly little interference between the tasks. The quasi-block task is a task where you have just blocks in front of you and the experimenter taps the blocks in a certain order. You have to watch that, and after a given delay, the retention period, you have to tap them again in the same order. So you have to memorize the spatial arrangement of the movement. Okay, so that's what I just say. It's evidence that you have two distinct systems because you have very little interference between verbal and visual spatial tasks. So they found good evidence for these distinct systems. Of these ones. There's not that much research so far on the episodic buffer. I'm sure Baddeley has also done something on that, to say that this is an independent system as well. Okay, let's look at the phonological loop in a little bit more detail. This is short-term memory basically for speech-based information. And it consists of two components actually. So you can further divide it down. The phonological store, and this holds items just online in a passive way. We can put words there, letters, a phone number or something like that. But if we don't do anything with that, information will decay very quickly and we can't access it. So basically we have forgotten it. And the time frame for that is roughly 2 seconds, unless we refresh it. And the refreshing is the rehearsal process. So when you do this type of task, and in your mind you say, fashion indoors, whatever, fashion indoors, whatever, what you actually do is you rehearse and you refresh the memory representation here in the phonological store by using the rehearsal process. And as you know from yourself, when you do these type of tasks, you do that kind of in an item by item way. So you go through the items to bring activation up again with the next one and the next one. And this is a little bit like these artists in a circus or so, which have these plates spinning on sticks. And what they have to do is give it a good spin, go to the next one, give it a good spin, go to the next one, and so forth. And if we exceed our capacity, it's the same as they tried too many plates. When they gave a good spin to the last one and the first one became too slow, it will fall down. In terms of our memory, this means the activation level decreased so far so that we forgot it and it's not part of our short-term memory anymore. So that this model actually predicts, we will see that later, that we may have a time limit on the information we can store. We have to be quick enough to go through every item to reactivate it. Okay, so the visuospatial sketchpad is a little bit similar to that, but also shows some differences in its architecture. So this is for visuospatial information. It usually has less capacity, 3 to 4 items. And we also need rehearsal to prevent the decay. Again, this time Logi proposed 2 subcomponents, the visual cache, which holds the visual spatial information, and something which is called the inner scribe, which carries out cognitive operations or manipulations on this information. So for instance, rotating an object, when we do mental rotation tasks, then this works in the inner scribe. And the visual spatial sketchpad has separate mechanisms to process information which is of different nature. And this is visual format, for instance, form of things, and spatial format, like the Corsi block task. So this is, again, a further breaking down and subdistinction, spatial and visual information. Now, suppose you want to do a study on your visual spatial sketchpad, and you're interested in what is the memory for visual information, for form information. And how would you investigate that?
I just recently did an Alzheimer's test online. I think it did with a matrix with day-to-day objects in some of the cells, and then get you to recall later what the objects are and which row of the matrix they were in. Okay,
yes. This is about, there's a lot of spatial information in there. Let's say you would just do the objects. And what objects did they use?
Things like tennis rackets, cars, aeroplanes.
Okay, so suppose we have a study and you provide a tennis racket and a car and a ball. Do you really test visual memory? How do you retain or do you try to remember the information? Yeah, you would code that semantically. You would say in your mind, in words, car, tennis racket, and so forth. So what is the big challenge if you want to do these type of studies?
It must be a pattern, random pattern.
Random patterns, possibly.
Do they often do it with it's a grid and then there'll be certain coloured blocks amongst the grid and you have to remember the place of the block on the grid?
Well, then you're again in the spatial domain. It's just about form, just shape of things. Where the challenge is, you have to find shapes which you can't verbalize. Where you can't say, oh, this looks like this, or this looks like an M, or something like that. And people are really creative about this. And in the Western world, what people often use is, for instance, Chinese characters. And just make sure that people don't speak Chinese, of course, because they are very hard to verbalize. What other people have used is they went to Star Trek and used the Klingon alphabet, because they have a lot of shapes which you very hardly can verbalize in a way as well. So you have to come up with abstract shapes where people can't say, oh yeah, this is the S shape, this is the T thingy like, so that you really are investigating only form and shape and not semantic memory. That's the big challenge in this type of research. Okay, do you have any questions on that bit? Okay, so I would like to have a look, and this is the last section for today, a little bit of a closer look at verbal short-term memory, because this is one of the best investigated types of short-term memory, because it's easy to investigate, as we just have seen, as opposed to the more visual spatial types, and it's very relevant for our everyday life. So in terms of the models we have spoken about, the verbal short-term memory, well, in Cowan's model, it's just part of long-term memory. He didn't propose that we have a dedicated verbal short-term memory. Atkinson Shiffrin as well said it's just short-term memory, not split by domain, while the Baddeley model says, well, that's phonological loop. Okay, let's start again with a demonstration. And I would like you to ask to remember the number I will tell you in a moment. Okay. Everybody ready? 39175. And please write it down now. Okay, another demonstration. There will be a number on the screen in a moment. Try to remember it, and only when it comes up, please write it down. Just wait. Too easy for immediate recall. Try to rehearse it. Okay, now write it down. Okay. How did you do the task? When you heard the numbers?
Just rehearsed it.
Rehearse it in your mind, yeah. Okay.
I made associations because I got married in 1995 and my children was born on the 17th of the month.
Yeah, okay. So you try to chunk as good as possible. But the usual strategy is to rehearse. So you say them verbally in your mind. You say 9157, 9157. How did you do the task when you saw the numbers on the screen? Did you try to keep the visual image in front of your eyes? Would be a natural thing to do, you would say. It's a visual information. So why not just keep the visual information online? But we don't do that. We usually rehearse again, verbally in the same way. So this shows that verbal information is encoded in a format of a series of sounds, acoustically, even when it's presented visually. So it's a very strong thing which we do, and which we had before with the pictures as well. Whenever we can, we try to put it into an acoustic format for short-term storage. So there's quite a bit of evidence that we actually do this phonological encoding of verbal information. One study, a very early study done by Conrad in 1964. So it's a series of 2 studies which you need together to see the evidence. In the first study, participants had to recall just spoken letters which were presented with a lot of background noise. So people were recording the letters and then they were adding artificial noise to that. And what happens if you add the noise, and you know that probably from yourself, if you want to spell something over a bad phone line, that acoustically similar letters are sometimes or often confused. So when you're on a bad phone line, it's very hard to distinguish M and N and B and P with each other. So you have acoustic confusion here. Now the second study, he presented participants letters visually to remember them. And what happens is that you observe the same type of errors. Letters which are acoustically similar, for instance M and N and B and P, are often confused. And the interpretation is that we do this acoustic rehearsal, and our rehearsal system, it's not a perfect computer. We have some noise in our system as well, so that we do these type of confusions. So this finding again supports the idea that we really do this phonological encoding of verbal information. Okay, so we already discussed that before, but now we come from a different area. We just said, okay, we have phonological information. Does that maybe affect the number of items we can store? So let's have another demonstration, another little test. So again, you will see 5 words. They will be names of countries. And please try to remember them, to encode them while they're on screen. When they disappear, try to rehearse them, and only when it says on the screen, write them down again, okay? So there will be a retention interval. Okay, are you ready? And go. Okay, was it difficult? Not too difficult. It was 5 words. So according to what we have learned, 5 chunks below the 7 plus minus 2. So fairly easy. The chunking hypothesis says as long as it's 5 chunks, it should be the same difficulty, shouldn't it? So I will present you another 5 words. Same task again. Okay, these were the 5 words, by the way. Okay, demonstration 2. So chunking hypothesis will tell you what comes up now will be as easy as the other one. Okay, so these were the 5 words. Was the task easier or more difficult? Who found it more difficult? Raise your hand. Okay. Who found it easier? Okay, nobody. Okay, good. So, this is in some kind of disagreement with the chunking hypothesis. However, it is in agreement with what we have heard about how verbal working memory is working. And the idea is that we do the phonological encoding. We have to speak them in our mind to rehearse them. And this is the so-called word length effect. Because the words are longer, it takes longer to pronounce them, it is easier, a bit more difficult for us, or we can store less. And, okay, that was crap what I just said. The longer it takes to say the items, the less items we can remember. That is the word length effect, and that is a very robust finding which has been reported a lot of times. And research has shown that the time limit is estimated to be around 2 seconds. So everything which we can say and squeeze in 2 seconds, we can remember. So if we have short words, we can remember more as compared to long words. Okay. So that's what we have just seen. And there is some merit to that. For instance, it has been shown that there are differences between languages. So in a language like Welsh, where it takes longer to say certain numbers, people have on average a slightly lower number span in Welsh as compared to English. And the interesting point is when you have bilingual speakers, you find this difference in the same person. So that a person, okay, can we come a little bit quiet now again? I know we are getting close to the end, but it's unfair to the people who actually want to listen. Okay, thank you. So that actually reflects that. And it has been shown that, for instance, Welsh people score slightly lower on certain mathematical tasks, but just because it takes them a little bit longer in their mental arithmetics to deal with that information, so they have a slightly lower memory span for that. That doesn't mean they're dumber or anything like that. It just means it's an effect of the language you speak. Okay, so what is our short-term memory capacity? Baddeley says basically everything which we can say within 2 seconds, and Miller suggested, well, it's 7 plus minus 2 chunks. So this is somewhat conflicting. It may be that on average it's roughly 7 things we can say in 2 seconds, so that there some equivalency comes from. However, there are a few studies, not too many, which tried to combine that and put that together. And it has been shown that short-term memory capacity actually depends on both. So both is true and has its merit, if you want to say. And the fact is, so it's the number of chunks and the number of syllables within each chunk. So what these studies are trying to do is to independently vary from each other the number of syllables and the number of chunks. And this can be done in some languages, such as Chinese, where you have these characters, where you have one character which forms one chunk, but which may have different number of syllables. And then you can investigate the effect of each other, and you can see that both of them have an effect. So both concepts affect our short-term memory, but they do interact with each other, so they have to be taken together. And if you increase the size of chunks, and by this what is meant is that a chunk is longer, like in the beginning where we said, okay, now we have a chunk of just of a word, and now we have a chunk of a whole sentence. You can do that on a lower level, say by the number of syllables. You can have a chunk of short words or long words, for instance. So if you increase the size of the chunks, then coming from this chunking hypothesis, what you observe is that you recall less chunks. So the quality of the chunk also determines your capacity. For like an average chunk, it may be 7 ± 2 for certain materials, but when you create very large chunks, you will see that this number goes down. However, it is a little bit less than expected by what you predict there. However, if you increase the size of the chunks, what you also can do is you can recall more syllables beyond the 2-second limit proposed by Baddeley. So both effects are at work here and interact with each other. And there are actually computational models which found the exact parameters of the weighting and how much in milliseconds each contributes to this joint process. Okay, do you have any questions on that? Okay, yes.
Is there an advantage for multilingualism in this case?
In which case?
In terms of the ability to chunk.
Well, bilinguals or multilinguals often have an advantage in executive functions. Whether they have this helps in chunking, I'm not too sure, because chunking is just retrieval of long-term memory structures, and that's not necessarily better in bilinguals, I would accept. Okay, then thanks for coming. Next week we speak about long-term memory and learning. Okay, have a nice week. See you then.